So I would like to announce our next speaker. It's Mátyás Domokos from Alfréd Rényi Institute of Mathematics of Budapest, and he will talk on the classification of moduli spaces of quiver representation. Please, Mátyás.
Thank you, and thank you for the possibility to speak here. So quiver representations were mentioned already in a few talks, but I need to go into the details a bit more. So a quiver is just a finite directed graph. Q sub 0 will stand for the set of vertices and Q1 for the set of arrows. And I shall denote by, for an arrow A, S of A, the source of the arrow, and T of A, the target of the arrow. So S and T are maps from the arrow set to the vertex set. And a representation of the quiver Q is a collection of vector spaces and linear maps. To each vertex, we associate a finite dimensional vector space, and to each arrow, we assign a linear map from the vector space attached to the source of the arrow into the vector space belonging to the target of the arrow. And we call the dimension vector of the representation R the values, the collection of the values of the dimensions on the vector spaces associated to the vertices. And the representations of a quiver form a category where a morphism between two representations R and R prime is a collection of linear maps for each vertex of the quiver. We take a linear map between the vector space associated to that vertex by the first representation into the vector space associated to that vertex by the second representation, in such a way that for each arrow A, this diagram of linear maps commutes. And by a subrepresentation S of a representation R, we mean a collection of subspaces SV of the vector space RV associated to the vertex V by the representation R, in such a way that the linear map R of A must map the vector space belonging to the source of A into the subspace S sub TA belonging to the target of A. So this should hold for all arrows in the quiver. And then, of course, it makes sense to restrict the linear maps R sub A to the subspace S sub source of A, and we get a representation of the quiver. And the next thing to recall is the notion of representation spaces. So we fix a dimension vector, alpha. So it's just a collection of non-negative integers associated to the vertices. And we shall denote by rep Q alpha and call the space of representations of Q of dimension vector alpha a direct sum of spaces of matrices. For each arrow, we take matrices whose size is given by the values of the dimension vector on the target and the source of A. So this is just an affine space. Its elements are thought of as collections of matrices of various size, and there is a natural action of the so-called base change group, the product of general linear groups. We take for each vertex the general linear group of size given by the dimension vector, and here is the rule of this linear action of this reductive group. So for example, if you just take the two-loop quiver, so it has one vertex and two loops, then the representation space is for the dimension vector n is just the space of pairs of n by n matrices with the simultaneous conjugation action of the general linear group. Or another well-known classical case is the case of Kronecker's matrix pencils. So the quiver has two vertices this time and two arrows from the first vertex to the second. So again, the space of, we take the dimension vector, nn, for example. There is a typo here, so this should be nn. It's again the space of pairs of n by n matrices, but the action of the group is different, and it's the direct product of two copies of GLN, and here is the rule for the action. And the aim of the general aim of quiver representation theory is to classify representations up to isomorphism, and to a point x in the space of alpha dimensional representations of Q corresponds a representation which I denote by Rx. So we take just the vector space of column vectors of length alpha of V. This is the vector space associated to the vertex V, and the linear map associated to the vertex A is just multiplication by the matrix component of X associated to the arrow A. And it's clear that for any alpha dimensional representation of Q, there exists a point X in the representation space such that Rx is isomorphic to the representation we started with. And moreover, 2 points X and Y in the representation space correspond to isomorphic representations if and only if they have the same orbit under the base change group. And so we want to classify representations. So for the approach of invariant theory is that we would like to have varieties parametrizing the orbits. And the first approximation of this problem is given by so-called affine quotients. So we take the algebra of polynomial invariants on the space of representations, and the comorphism of the embedding of the subalgebra of invariants into the full coordinate ring of the representation space gives morphism from the representation space into this quotient variety, the spectrum of the algebra of invariants. So that's what's called affine quotient. And let me recall that the algebra of invariants, the generators of this algebra of invariants was described by Lebrun and Procesi in 1990. So the result is that this algebra of invariants, the algebra of GL alpha invariants on the space rep Q alpha, is generated by traces of oriented cycles in the quiver. So an oriented cycle is just a sequence of arrows A1, A2, AN in the quiver, such a way that each arrow in this sequence starts, the target of an arrow in this sequence is the source of the next arrow. And of course, the nth arrow's target is the source of the first arrow. And for such a sequence, if you take the product xan minus 1, xa1 of matrices, we get a square matrix or a linear transformation of the vector space associated to the source of A1, and we can take its trace. And it's obviously a polynomial function on the representation space, and it's invariant. So, for example, from this description of the generators, it's clear that if a quiver has no oriented cycles, then there are no non-trivial, non-constant polynomial invariants. And then this affine quotient space is trivial. It has just one point. And so we would like to have some more so we would like to turn next to another construction of quotient varieties, which gives something non-trivial also for quivers with no oriented cycles. So we will call such quivers acyclic. And let me recall the construction of Alistair King. So first of all, we shall call a weight an assignment of integers to the vertices of the quiver. So weight is just a tuple of integers. Negative integers are allowed this time, so not like for dimension vectors. And given such a weight theta, we say that a representation is theta semi-stable if the sum over the vertices of the values of theta and the value of the dimension vector gives 0 on one hand. On the other hand, the corresponding sum for each sub-representation of the quiver is non-negative. And a non-zero theta semi-stable representation is called theta stable if there is no proper non-zero sub-representation S of R such that this sum over the vertices of the values of theta and the dimension of the dimension vector of the sub-representation on the value on the vertex V is 0. So it's always positive. So this sum is always positive for all proper non-zero sub-representations. Then we say that R is theta stable. So the theta semi-stable representations of Q form an abelian category in which the simple objects are the theta stable representations. So in turning back to the representation space, we can take in the representation space for a given weight theta consisting of those points x such that the corresponding representation of is theta semi-stable. Well, it turns out that this subset is Zariski open, which contains, again, as an open subset, the points which correspond to theta stable representations. And the theorem of Alistair King from 1994 says that there exists a good quotient of this open subset of the representation space consisting of the theta semi-stable points by the action of the base change group. So this means that there exists a variety and a surjective G-invariant morphism from the subset of theta semi-stable points such that it's an affine morphism. So if we take an affine open subset of the target variety, its preimage is an affine open subset here, and the restriction of pi to this affine subset is the affine quotient, which was introduced before, so which is given by taking the spectrum of the algebra of invariants. And moreover, the restriction of this map pi to the subset of theta stable points is a so-called geometric quotient. So it's the fibers of this the restriction are just the orbits. So in general, the fibers of pi also have a nice description, namely x and y have the same image under pi if and only if the corresponding representations have the same theta stable composition factors in the category of theta semi-stable representations. So the construction of these quotients involves relative invariance. So with the weight theta, we can associate a character of the base change group, namely I denote by high sub theta of G. Its value is the product over the vertices, the determinant of the component of the group elements belonging to V raised to the power theta of V. And a relative invariant of weight theta of the base change group on the coordinate ring of the representation space is just an element which has the property that an element F which has this property that F of Gx is F of x multiplied by the value of the character on G. So such a relative invariant is an absolute invariant for the commutator subgroup of the base change group, which is just a product of special linear groups. And if we take the subspaces of relative invariants whose weight is n times theta for n equals 0, 1, 2, and so on infinity, the sum of those subspaces, which is of course direct, is a subalgebra of the algebra of SL alpha invariants. So we shall denote it by S sub theta Q alpha. And this will be viewed as a graded algebra. The degree n homogeneous component will be the space of relative invariants of weight n times theta. And King shows that this subset of theta semi-stable points in the representation space is the complement of the common zero locus of the relative invariants whose weight is n times theta for some positive integer n. And this good quotient variety, which we introduced before, from now on, we shall denote it by m sub theta of Q of alpha, and we shall refer to it as the moduli space of theta semi-stable representations of Q with dimension vector alpha. It's constructed as the projective spectrum of this graded algebra, whose homogeneous components are the spaces of relative invariants with weight a multiple of theta. So the degree 0 component is just of this graded algebra is the algebra of GL alpha absolute invariants on the representation space, which is just the base field when the quiver is acyclic. So in that case, this moduli space is a projective variety. In general, it's a quasi-projective variety. So if we allow oriented cycles, this moduli space is a quasi-projective variety. this can be done in a more general context of quivers with relations, where we don't consider all representations of the quivers, but we specify certain relations. So the relations are certain linear combinations of passes in should give 0. And in that case, it turns out that all projective algebraic varieties can be realized by this construction. So any projective algebraic variety is isomorphic to a moduli space of representations of a quiver with relations. So this was proved by Hille, Hisgen, Zimmermann. Or there is another construction related to quivers, which establishes a connection with algebraic geometry, the notion of quiver-Grassmannians. And again, any projective algebraic variety can be realized as a quiver-Grassmannian. This was observed by Rényi, Hisgen, Zimmermann, and several other people had variants and refinements of this result. On the other hand, it's quite easy to see that the number of projective algebraic varieties up to isomorphism that occur as a moduli space of representations of some quiver is countable. So this leads to questions about possible classifications. So for example, given positive integer d, how many d-dimensional projective varieties can be realized this way as a moduli space of quiver representations? And how large quivers and dimension vectors are needed to realize them? And in particular, is it true that for each positive integer d, there are only finitely many projective varieties which occur as a moduli space of quiver representations? And it's known, it follows from results in the literature that if we restrict to tame quivers, then all possible moduli spaces are affine spaces or projective spaces. So we should focus on wide quivers. And two more remarks. So a one-dimensional projective variety, the projective line is the only one-dimensional projective variety which occurs as a quiver moduli space. So this is an observation of Yiru Fei. Another result is that if we take a very special dimension vector which takes constant 1 on all the vertices, which is 1 on all the vertices, so this is very special, but it's an interesting special case because in that case, these moduli spaces has a natural structure of a toric variety. And building on some earlier results of Altman and others, with Daniel Yo, we proved that for each positive integer d, only finitely many toric varieties can be realized as such a moduli space. So at least in the toric case, we have a positive answer for this question here. And to study these questions, we can reduce to stable dimension vectors because of the following results. So first of all, we call a dimension vector alpha theta semi-stable if there exists a theta semi-stable representation of dimension vector alpha. And similarly, we call the dimension vector alpha theta stable if there exists a theta stable representation of dimension vector alpha. And then we have the following theorem, which is a corollary of results of Derksen and Weyman and also Colin Kinrich, that and some known results on moduli spaces of tame quivers, that a projective algebraic variety X occurs as a moduli space of representations of a quiver if and only if it's a product of factors where each factor is a projective space or is a moduli space of a wide acyclic quiver with a stable dimension vector, stable for some weight. So we have projective spaces, moduli spaces for weights and dimension vectors where the dimension vector is stable with respect to the given weight and products of such varieties. Now we need to recall some facts about dimension vectors. So first of all, the Cartan form on the it's a bilinear form on associated to the quiver Q, whose value on a pair of dimension vectors is given by this formula. So we take twice the sum over all vertices, the values of the two dimension vectors, and we subtract a sum for each arrow A. We take the product of the value of the first dimension vector and the second dimension vector on the endpoints of the arrow in both ways. So this is a symmetric bilinear form. And let's denote by epsilon v the dimension vector whose value is 1 at the vertex v and 0 on all the other vertices. So this is just these epsilon v's are just the standard basis vectors in set Q0. And then the so-called fundamental set consists of those dimension vectors which have these inequalities, that the value of the Cartan form on alpha and the standard basis vectors is non-negative. So this is a subset of the dimension vectors defined by finitely many linear inequalities. And moreover, the support of alpha, for an alpha in the fundamental set, its support has to be connected. So by the support of a dimension vector, we mean the full subquiver, which is spanned by those vertices on which the dimension vector is positive. The reason we record the fundamental set is that it's easy to see that if a dimension vector is theta stable, then the general representation of Q with that dimension vector must be indecomposable. So such dimension vectors are called Schur roots. So such a dimension vector must be a so-called Schur root. The dimension vectors of the indecomposable representations, called the roots, were described by a famous theorem of Cutts. They fall in two classes, the so-called real roots. These are the dimension vectors contained in the Y group orbits of the standard basis vectors. And there are the so-called imaginary roots. These are the dimension vectors contained in the Y group orbits of the elements of the fundamental set. And moreover, the elements of the fundamental set which have wide support are Schur roots. So therefore, well, the real roots give only one-point moduli spaces. And given this description of the roots and this information about Schur roots, I think it's natural to focus first on Schur roots in the fundamental set. And that's what we will do. And here is our main result. We can prove that for any positive integer d, up to isomorphism, there are only finitely many algebraic varieties X of dimension at most D, which can be realized as a moduli space of quiver representations in such a way that the dimension vector is taken from the fundamental set and it is theta stable for the weight. Unfortunately, there is a typo here. So this should be the moduli space M theta Q alpha. So this is a partial result on this question about the finiteness of quiver moduli spaces in a given dimension. So with this constraint on the dimension vector, namely that it belongs to the fundamental set and it's theta stable, we do have a finiteness result. So in order to set some consequences, let's denote by X a set of representatives of the isomorphism classes of the moduli spaces covered by this theorem. And it turns out that if Q so let Q be an acyclic quiver, and suppose that the dimension vector alpha satisfies any of the following two assumptions, that it's bounded by 2 on each vertices, or it takes the constant value n for each vertices. The number of isomorphous classes of moduli spaces that can be realized with such dimension vectors is finite. So of course, the assumptions on the dimension vectors here are very restrictive, but at least this is a direct generalization of the result on the toric case, where the assumption was that the dimension vector is constant 1. So instead of constant 1, we can assume, it's enough to assume that it's at most 2 everywhere, or it's the same everywhere. And we have this finiteness result. So this is the corollary. And now let me turn to the proof of these results. So we need to introduce some terminology. So given a quiver and a dimension vector alpha, sincere just means that it's everywhere positive. So it takes positive value on all the vertices. It's easy to see that it's sufficient to restrict to such Q alpha pairs where alpha is positive everywhere, because we can forget those vertices on which the dimension vector is 0. And let U be a vertex such that there is no loop at this vertex, and we will say that this U is a so-called large vertex for the pair Q alpha if the dimension vector alpha satisfies this property, that its value at U is greater than or equal than the sum of its values on the sources of all the arrows whose target is U, and similarly the value of alpha at U should be greater than or equal than the sum of the values of the dimension vectors of the targets of those arrows whose source is U. And for such a vertex, so if U is a large vertex for the pair Q alpha, then we define an operation denoted by tau sub U. So tau sub U of Q alpha will be the quiver dimension vector pair, which we obtain by the following way. We remove the vertex U and all the arrows adjacent to U, and for each pair of vertices B, C, where B goes into U and C starts at U, you will replace this pair by a new arrow, D, from the source of B to the target of C. And tau sub U of alpha is just simply the restriction of alpha to the vertex set of this new quiver. And we shall need another operation as well. So for this other operation, U has to be a source or a sink. So U, either all arrows adjacent to U, either there is no arrow whose target would be U, or there is no arrow whose source would be U. In the first case, U is called a source. In the second, it's called a sink. And under the assumption that the value of the dimension vector on U is smaller than the sum of the values of the dimension vector on the vertices, the neighboring vertices, then we will define sigma U of Q alpha as the pair where in the quiver we reverse all the arrows adjacent to U, and the dimension vector we perform this transformation. So the dimension vector remains the same for all vertices different from U, and at U we take the difference of the two sides in these inequalities. So we subtract the alpha of U from the sum of the alphas at the vertices adjacent to U. So this is a so-called reflection transformation. So this Y group mentioned before, which acts on the space of dimension vectors, is generated by exactly these transformations given here. So here is an example. So the first, we take a quiver, we have here a part of a quiver, and the dimension vector. So U, in this case, is a small sink. So we are allowed to reverse this arrow, and that's how we get the second quiver. So now the arrow starts at U and ends at W, and the value of the dimension at U was originally 2, but now it will be 5 minus 2, so it's 3. And observe that for this new quiver, quiver dimension vector pair, W is a so-called large vertex, yeah, because there are two arrows ending at W, and 1 plus 3, so the value of the dimension vector is smaller than the value of the dimension vector at W, and there is only one arrow going out, and 4 is smaller than 5. So we are allowed to perform the operation tau W. So we remove W and replace these two, the path from U to this vertex by a single arrow, and similarly this path by a single arrow. And we got a smaller quiver, a quiver which has one less vertices, and also the total dimension is smaller. So this leads us to the notion of tau sigma minimality. So given a class of quiver dimension vector space pairs, we say that a pair is not tau sigma minimal if by a sequence of such operations we can reduce to a smaller pair, smaller in the sense that it has fewer number of vertices, or it has the same number of vertices, but the total dimension is smaller. And we have this theorem that suppose that Q prime alpha prime is obtained from the pair Q alpha by applying such a transformation, tau u, where u is a large vertex, or sigma u, where u is a small source or a small thing. Then, for any weight theta, there exists a weight theta prime such that the algebraic varieties m theta q alpha and m theta prime q prime alpha prime are isomorphic. And moreover, if alpha is theta stable, then we can choose theta prime in such a way that alpha prime above is also theta prime stable. So the proof of this result uses classical invariant theory. For the second statement about stability, we need some basic facts on the geometry of representation spaces. And let me know the first statement for the case sigma is due to Katz and Skowronski-Weyman. And I think my time is over, so I cannot say more about the proof. Just one sentence maybe, that the advantage of working with dimension vectors which are stable is that we have a combinatorial formula for the dimension vector of the corresponding moduli space, because it's given by 1 minus 1/2 times alpha alpha for the Cartan form. Yeah. So, but I have to stop here. So thank you very much for your attention.
Thanks a lot for your talk. Are any questions or comments, observations? Well, I have another very naive question. Maybe it's not exactly related to your talk, but for example, we can consider, let's say, simple representations or semi-simple. Let it be semi-simple representations, and if we are of fixed dimension, and if we are asking. Okay, I will ask, and then Karen, you will ask. And if you're asking about separating invariants in this case, so we are not considering all representations, but maybe just semi-simple. Will it give us some additional benefits if we will try, let's say, we'll try to consider separating invariants, for example?
I don't know.
Okay, but if we will try to do the same with stable, semi-stable,
So,
it will not.
So if you take the zeros weight, then semi-stable corresponds to semi-simple and stable to simple.
Yes, yes.
It's a special case.
Okay, then, Colin, your question. Please turn on the microphone. Your microphone is off. No, we can't hear you. Yes, now it's on.
For some reasons my headphones are not working properly. So I wanted to ask you about this list X that you mentioned early on. And so you said that you have this list of representatives of varieties, and then a moduli space somehow shows up on that list. Do you have some insight on how many representatives you have? Is the number of representatives on that list bounded, I don't know, by a polynomial of n or d? I believe the dimension. Yeah, that's right. That's the theorem. So you fix d, and then you have this curly x, which is a set of representatives. And I mean, can you say anything about the items that show up on X, and also the number of items in that list?
Yeah. So here is the point is of this theorem, which I had no time to explain, is that if in that list you can give an explicit bound on the quiver and the dimension vector, depending on the dimension. So D is fixed, this number is fixed.
Right.
And then we have an explicit bound on the number of vertices of the quiver you have to take on the number of arrows and the values on the dimension vector, just in terms of D. So this gives a bound. You get everything just using quivers with only that many arrows, that many vertices, and with dimension vectors which are bounded this way. But of course, for each per Q alpha, you have finitely many possibilities for the weight.
Correct.
In principle, it could be worked out how many, but
yeah. And in the case when I believe you stated a result where the dimension vector was at most 2 at every vertex, that was one of the allowable case. And the second case, I believe that the dimension vector was supposed to be constant n.
Yes.
Right. And then you said that the moduli is isomorphic to a product of varieties from X. At least in the case when the dimension vector is at most 2. Were you able to check that the varieties that show up are all rational varieties?
I haven't thought about it, but in fact, so I used your theorem, by the way, said, and I haven't stated in that form, but you just from X, you just need to take such elements which also satisfy these conditions.
Right. But I guess this goes
the stable decomposition. Also, in that case, it's clear that it has this property in the other case as well. So, in fact, you have a stronger theorem what is stated here, and I haven't thought about this rationality of this class.
Because they are conjectured to be rational. That's the famous rationality conjecture. It has been open for so many years. But I was wondering if in the case when the dimension vector is at most 2 at every vertex, whether you could see if the corresponding moduli is rational or not.
Yeah, maybe because there is this result of Schofield which establishes a birational isomorphism between matrix invariants, and probably the matrix invariants will be, so the matrices will have small size.
Right. I see. Yeah, very good. Thank you.
Okay, are any further questions or comments? Okay, let's thank the speaker again.